I'm George Self. This video is one in a series designed to help with the R labs for BASV316 Introductory Methods of Analysis. This is Lab 8, Visualizing Data. Data are usually much easier to understand if we can draw a picture. If we can put the data in some sort of visualization, then we're much easier to understand than, say, a whole bunch of numbers in a table someplace. For example, this is a histogram. Now, a histogram takes a lot of continuous data, divides it up into bins, and then counts the frequency of all of the values in each bin. For example, here I have the New York City temperatures taken from the air quality data frame. Now, these are the summertime temperatures over the course of one summer. Notice that some of the temperatures were fairly low, down in the 60s, a couple were pretty high, but most of the temperatures were in the middle, around 80 degrees. This would be what's called a normal distribution, where most of the values are in the center. As another example, we have a beaver data frame where the body temperature of a beaver is listed over the course of several weeks. You'll notice that this body temperature in general stays near the center, and with just a few temperatures out at the extreme. Again, this would be a normal distribution. The rock data frame provides us a shape, a bunch of data, the rock shape data. This does not look like a normal distribution. Notice that most of the values are clustered here in a lower end with only a few values at the upper end. And finally, rock perimeter. This would be what's called a bimodal bunch of data. That is, there are two groups of rocks. There are rocks with small perimeters and rocks with large perimeters with not many in the middle. Creating a histogram in R is fairly simple. The script that you see here is similar to the scripts we saw in other visualization labs. If I run this, you'll see that it draws a histogram. This is Morley's speed of light experiment. Let me get this up here where you can see it a little bit. This would be a normal distribution. Most of the values are near the center with a few values out towards the extremes. If I copy this script and paste it in here, I can then look at U.S. judge ratings, INTG variable in there. The main title is U.S. judge ratings. The x-axis is going to be integrity rating. The y-axis is going to be listed as frequency. I'm looking for 11 breaks. That's how many bars we're going to get across there. I want 8 colors from the CM Colors palette. That should do it for us. Let's run that. And there we go. There's our U.S. judges ratings. And it's a histogram. And this, by the way, is not a normal distribution. Most of the values are clustered up here near the top with very few values near the bottom. But that's all right. I'm going to copy this because next we're going to submit our deliverable. For this, we're going to go with the cafe data and the age vector in there. The title is going to be histogram. The x-axis will be labeled age. The y-axis label will be frequency. For our histogram, we want 10 breaks, and the colors will come from the topo palette. We'll look for 12 colors out of there. And run. And there we go. This would be the deliverable for histogram for our class. Next is a density plot. A density plot is actually almost exactly the same as a histogram, except it's all been smoothed out. These are the same New York temperatures we saw earlier, and you can see here a very clear normal distribution. Most of the values clustered up near the middle with only a few on each side. That rock perimeter, remember I told you that was a bimodal distribution. You can see that clearly here. Lots of rocks with small perimeters, lots of rocks with big perimeters, and not much in the middle. Our demonstration for a density plot, we're using some crime data from the United States, arrest records here. This is not a bad distribution. It's clustered a little bit towards the low end, but that's all right. That would be a normal distribution. I'm going to copy this and paste it in here. We're going to want the U.S. judge ratings and the integrity vector in there. We're going to name this U.S. judge ratings. The x-axis is integrity rating. Y-axis is density. LWD, that's the width of the line, is 2, and our line color wants to be blue 4. And let me run that. There we go. And that's again a nice normal distribution. I'm going to copy all of this. And now for our deliverable, we're going to be using the cafe data frame because that's what I always use. And the age vector in there. Main title is density plot. X label is age. Y label's density. Line width is 2. And the color is going to be cadet blue 4. Run that. And there's our plot. Again, a nice normal distribution. Next, we're going to take a look at line graphs. Line graphs are used to record time series. My first example here, you'll notice passenger air miles from about 35 or something up until 1960. Unsurprisingly, the number of passenger air miles increased during that period of time. I have here a graph that shows the accidental deaths in the United States over a period of time from about 1973 to 79. These were recorded each month, and you'll notice in the summer months that there's a spike, and in the winter months a trough. And we would expect that more people die accidentally in the summer than in the winter. Another example was U.S. presidential approval ratings, and you can take a look at that. Our demonstration graph is a graph that shows lung disease deaths over a period of time. And you'll see that this graph shows pretty clearly that during the winter months that the lung disease deaths spikes. I'll copy this. And now we'll go down to guided practice. I'll paste that in here. And for this, we want the UK gas data frame. UK gas is United Kingdom heating gas usage. So the title will be UK quarterly gas consumption. The x-axis label is year, and the y-axis is millions of therms. The type of graph L, that's not a 1, it's an L, it's for line. The width of the line is 2, and we want the color of the line to be light sky blue. And if we run that, you can see that in general the gas consumption in the United Kingdom has increased over the period of time, and that as time goes on, the amount of gas used in a winter becomes very greatly distanced from the amount of gas used during the summer. I'll copy this because next will be our deliverable. And for this, we're going to be using the links data set because this is a nice time series. The title will be line graph. X-axis is year. Y-axis label is number. This is an L, width of 2, and the color for this line will be fire brick 4. Let's run this. And that's what your graph should look like. This shows the number of lynx cats that were trapped over a long period of time there. Next is a plot. These are often called scatter plots, sometimes even dot plots. We simply plot two variables on the same graph or the same grid. For example, this first example here is the stopping distances of cars, up to 25 miles an hour, and then the stopping distance. The second example, I've added what's known as a line of best fit to the graph. So this shows the line that best describes all of those dots on the graph. This is a plot that shows Old Faithful eruptions. On the x-axis, you'll see the amount of time people had to wait for the eruption in minutes, up to 90 minutes. And on the y-axis, the eruption time for Old Faithful. This tells me that the longer people waited, then the longer the eruption. This also is a nice bimodal graph. It shows that there are some long eruptions and there are some short eruptions and not much in the middle. Now, all of the plots you've seen so far have been circles that are filled in. R, though, permits you to create plots with X's and crosses and triangles and all sorts of points. You can read about that in our lab. Here's a demonstration of a plot. You can take a look at that demonstration. However, I have a second plot here in a demo mode, and this plot includes a line of best fit, and this would be the one that you want to copy for later because we're going to be using the line of best fit on our future graphs. So let me just copy all of this out. Copy. And for the guided practice, I will paste this in. And our guided practice, we want to use the rock data frame. And the y-axis is going to be area. And the x-axis is going to be perimeter. The title for this plot is Rock Area by Perimeter. X-axis is perimeter. The y-axis is area. The type of point I'm using is 21. The background, that's the fill color for those points, will be golden. Rod 3, and the color, the circle, the line of the circle will be black. The line of best fit will have a width of 2, and the color for that will be violet red 3. Let's see if I got all that typed in right. Well, that looks about right. So that gives us a nice plot with a line of best, well, the line of best fit is off. How did that happen? Let me go back over here and see. Oh, I forgot to put in the right values here. This should be rock dot area and rock dot perimeter. That should look a little better. Now the line of best fit actually looks like it fits. So I do have now a good script. I'm going to copy this and paste it here. For this part of my lab, I'm going to use cafe. Bill is going to be on the y-axis, and length is on the x-axis. The title is line of best fit. X-axis label is length of meal. Y-axis label is bill. I'm using a 23 type of point. Indian red 4 is the color. Black is the circle color. The line of best fit is a line, and the color here is medium blue. And run that. Well, it looks like I messed up again. It's easy to do because the line of best fit was not there, and that's because I forgot to put the variables in here. Cafe dollar bill and cafe dollar length. And run that. That looks a little bit better already. So now we have a dot plot with a line of best fit. Yeah, that works well. Finally, a QQ plot. A QQ plot is used by investigators, by researchers, to try to determine if the data they are looking at is normally distributed. A normally distributed data set, these are those same New York City temps we saw at the very beginning of this lab. A normally distributed data on a QQ plot will form a straight line. And you can see this line, the circles that you see in this graph do form an almost straight line. The blue line there shows you the absolute perfect straight line. Here's that Old Faithful data. Remember, Old Faithful had a bimodal data where there were some long eruptions and short eruptions. Well, this is what bimodal data looks like in a QQ plot. Notice there's a lower area that's kind of flat and an upper area that's kind of flat, but there's a skip in between them. And altogether, this is not what you would call normally distributed. Finally, there's sunspots data. Now, we did not see this earlier, but I can tell you the sunspots data is very badly skewed. And you can see here there's a tail on the lower end of this QQ plot that goes out way far away from a straight line. This is not what you would call a straight line. Let's do a demonstration of QQ plots. And here they are. This is a nice normal distribution. These little circles are all pretty much in a straight line. That looks good. I'm going to copy this. Guided practice and paste that in. We want a QQ plot of the Swiss data set and fertility. Notice a capital F on that. The title should be QQ plot, Swiss fertility, and the red QQ line, and I'd better change this to Swiss dollar fertility, a red QQ line with a width of 2. Let's run that, and there we go. And again, I would call this a well-distributed normal distribution. All of those circles are pretty much in a straight line. There's a few oddballs near the lower end, but that's all right. So let me copy this, and now the deliverable for this particular section is a cafe data frame and age. Should have a title of QQ plot, just QQ plot, and the line should be, so I better change this to cafe $age, and the color of this line is Sienna 4. Let's run that. And it looks like the age data are normally distributed, and you can see the line of best fit in there. That's about it for this lab. Good luck with it. Again, if you get too hung up on it, please stop, contact me, and I'll be glad to help. I'll be seeing you online.